Okay. All right, so I have been waiting since energy and momentum, so not too long, but I've been waiting to do this question. I almost put it in our packet for momentum, but then I was like, oh, wait, it's got part A is a period question. We got to do simple harmonic motion first. Okay, so whether you call this a double topic, if you kind of lump simple harmonic in with energy, technically AP puts it separate, but triple double topic. They love to cross topic free response questions, even some multiple choice, okay? And so, you know, you can't just have a straight kinematic equation or topic question. They usually blend them. So just as a get ready for it. Okay, so this one, there's 7 points available. By the way, this is considered a short question. 3 short questions, 3 7-pointers on the AP free response. And then the other 2 are going to be your long ones, 12 pointers. Those are your lab-based and that thing called QQT. We'll see both of those in NMSI today. And so this one, about 13 minutes. I'm not going to set a timer, but by May, we got to be ready for it. And later on, this is going to be the paragraph length response. And so we've done these before. It doesn't tell us how many of the 7 points are here, but usually, you know, 5 to 6 points. I think A, since it's just determined the number, I'm going to guess that's 1 point. So maybe in the paragraph, and I know you're thinking it, oh, the checkbox is going to be a point. Usually those are not a point. It's all in the justification. And so maybe here we're looking for 5 or 6 physics ideas. Everybody good? Okay, so block P, which is the bottom, it's got a mass M. It's on a horizontal frictionless surface. It's attached to a spring with spring constant K. So just ignore block Q for the moment. The block P is oscillating with a period TP and an amplitude of AP about the spring's equilibrium position, and they do label it on the picture, and that's our equilibrium. A second block, Q, which has twice the mass, is then dropped from rest, and it lands on P at the exact moment that P passes through the equilibrium position. Okay, so it's a perfect drop. It's a perfect landing, right? Physics land. Block Q immediately sticks to the top of block P, and the 2-block system oscillates with this period T, PQ. I wish they'd given us numbers, right? No. And it has an amplitude A, PQ. And so part A is going to ask us, what's the numerical? Give us the number. And you're like, how can we do that? They didn't give us other numbers. It's, wait for it, you can. The ratio of the new period to the old period, okay? And so we need something about the old period, something about the new period. Hopefully, the first thing going through your mind is, oh, period of a spring, a mass on a spring is what? So what's the big idea that we're going to use? Exactly, 2 pi times the square root of m over k. I just need to apply this equation to the old and the new. And so for the new, T new over T old, we'll plug in 2 pi times the square root of our new mass and our new k divided by 2 pi times the square root of our old m and our old k. Now I'm using those subscripts just, you know, as an alternative. I could have done the P, Q, and P, which I will. Good question. Did they change the spring? No. So what's true about K new and K old? They're equal, right? And notice I got 2 pi over 2 pi. What's going to end up happening mathematically here? 2 pi is going to cancel top, bottom, and K new and K old, if they're the same thing, they're a denominator on both, aren't they going to cancel? Yeah. And so what are we left with? This ratio of new period to old period is really just the square root of M new over the square root of M old. So what's our new mass? After the second block lands on, it has a total mass of 3M. Yeah, you can put it as variable form. Divided by, what's our old mass? Just M. And so what happens? M's cancel as a variable. And what are we left with in the bottom there? Just a 1. And so what's our final answer here? Square root of 3. That's it. The ratio of TPQ to TP is just square root of 3. Final answer. Hopefully not too bad. And I think we'll look at the rubric here and I'll wait. Internal struggle. I think it was just worth 1 point, but possibly it was worth 2 points, and they're looking at the work leading. Did the student use the square root M over K type of equation, right? So always show your work, even though it's a numerical answer. Typically they don't reward students who just say, oh, final answer, square root 3. End of story. I cheated off my neighbor, square root of 3. No, and don't take a guess. Try to start with some physics idea and keep it going. Okay, so that's the newish piece, right? So using our new period equation of a spring. B, they repeat the picture. So FYI, the versions they release online, you're like, gosh, that's not a lot of room to write. It's a condensed version of what you get in May. Why do they repeat the exact same picture? In that year, it was on the next page. And so this was actually given over 2 pieces of paper. Is it a waste? I don't know, but it gives you more room to write. And so there you go. Big writers like myself, no fear, you'll be given enough room, I promise. Okay, B, same picture. The figure is reproduced above, so there they tell you duplicate. But beware, sometimes if you're given a new picture, they may make a change, right? So just always read. How does the amplitude of the oscillation, the new amplitude, PQ, of the 2-block system compare to the original amplitude, AP, of block P alone? So we're comparing amplitude new and amplitude old. Question mark. Is it going to be less than, greater than, or equal? Now, don't start with the checkbox, okay? You're not expected to know right off the bat the answer. I always save the checkbox for the end. And test taking strategy, I only check it if I'm confident, okay? Now, being a paragraph response, they will always read your paragraph, no matter what you check. But if it was one of the short answer types, if you're not sure on how to check it, don't check it, okay? Because if you check it wrong, they may not read your short answer. Hopefully that makes sense. Okay. In a clear, don't go mumbo jumbo and try to lose them in your jargon, right? Coherent, is it easy to flow? Does it flow? Is it easy to follow? You kind of want to put your physics down in sequential order. Paragraph, 5 to 6 sentences, 5 to 6 thoughts. Response that can also contain diagrams and or equations. So our typical physics, right? Explain your reasoning. And so what I'm going to do, I'm going to start with the physics. So what's going on here when you drop the top block onto the bottom? There's a collision. So first we say, oh, there's a collision. And Miss Earhart taught me that when there's a collision, what big idea has to go through my head? Momentum, right? What kind of collision is it? And so we want that big topic idea of momentum going through our head. And there's masses on a spring, which does have energy, and it has the new pieces with period and amplitude. And so the spring We're going to be using elastic potential energy, conservation of energy should be going through your head, right? And then that period and amplitude business. So these are just kind of like a roadmap on what we need to do. And so let's start with collision. What kind of collision is it? It says it sticks to it. Inelastic, if you want to get nitty gritty, it's a completely or perfectly inelastic collision. What do you remember about completely inelastic collisions? What kind of energy is not conserved? Kinetic. So KE is not conserved. But what is? Mechanical is not because of the collision. Mechanical is going to be because they gave us some caveats about a smooth surface, right? And so down here, mechanical energy is going to be conserved. But actually, for the momentum piece, when you have a completely inelastic collision, that has the most heat loss, right? So we've got the most heat loss. And so during the collision, we'll actually have a change in mechanical energy. But once they stick, due to the surface, mechanical energy is not going to be lost. So kind of piece it together. There's different parts here. Everybody good? Roadmap? So we need to figure out something about their amplitudes, right? Which is a distance that it stretches and compresses from equilibrium. And so remind yourself of that. It's the change in X max from equilibrium. And so that actually is found in our potential energy equation, US equals 1/2 K delta X squared. So we're going to end with that. So let's actually start with energy at the beginning of the drop. And so for the drop phase, we have a gravitational potential energy of which mass? Which Q is, which block is dropped? Q, sorry. Okay, so it's dropped in free fall, and all that potential energy is going to do what? Convert to kinetic of Q just before the collision, right? So it's going to have some kinetic energy, which, by the way, it's dropped vertically, but it's going to move horizontally. Does kinetic energy care? Does energy care about direction? No. So it does have kinetic energy before the collision. And then we have the collision. Let's write out our conservation of momentum statement, right? So in the beginning, now does momentum care about direction? Yes, momentum is a vector where energy was our scalar, okay? And so in the beginning, P is moving, right? It was already in motion when the collision occurred. And so we'll have the horizontal momentum of P initially. Horizontally, Q has none. After the collision, momentum is conserved. Now they stick together. And so it's the horizontal momentum of PQ final. And I can rewrite that in M and V terms. And so the mass of P and its horizontal initial velocity equals MP plus MQ and its final horizontal velocity. Good. Okay. And so after the collision, okay, after the collision, we got our two blocks. We're going to have this kinetic energy of the system alternate, because remember, it drops at equilibrium. And so this is at equilibrium. The kinetic energy of the system is all going to convert into what? What kind of potential? Elastic at one of the peaks, right? Whether it's going left, right doesn't matter. And so it's going to be at one of the peaks. And so elastic potential of the system at one of the peaks. What would that statement look like? Well, for the system, it's a collective, right? So this is 1/2 MP plus MQ. And the final velocity after the collision, so this is after the collision. I'm going to highlight to connect it. Those two are the same, right? Okay. After the collision, this is kinetic energy, don't forget to square, equals 1/2 K delta X squared. And K is based on the spring. That's going to be a constant, right? And this delta X, well, actually, I can erase that. What is delta X of your oscillation, your maximum? That's the amplitude we're looking for, right? So I need to compare this after the collision. So is it one of y'all? Not me, not me, not me.
Everyone should go, dude.
I think we'd hear more dinging if it was a school announcement, right? I don't think it's supposed to snow anytime soon.
Yeah, cross your fingers.
Video watchers, we've had phone dinging, and we don't know whose it is. I'm not opposed to y'all checking. If mom, is in the hospital or something, you need to know, right? No offense, mom. In our household, if y'all realize that if you watch enough Disney movies, Bambi, Frozen, it's always the mom well, I guess Frozen, both of them. But anyway, it's usually the mom that's not around, right? Nemo, yeah. Snow White, yeah, stepmom, Cinderella. Maybe it's just the classics. Maybe it's, Grimm. All right. Are dinging good?
Who was it?
I don't know. It's their business. It's okay. Okay. So here's the amplitude that we're trying to figure out. So in this new and old, just P, and then the PQ amplitude, tell me about K. Oh yeah, spring constant K. It's the same, so that's not going to affect the amplitude. Notice. Oh yeah. We can cancel out the. No, you cannot cancel the squares because they're on different things. One's an amplitude, one's a velocity. But then we'd have square root mass square root K. Yeah, not everybody's squared. Look at it that way. And so 1/2 can cancel out. And so A, amplitude is going to depend on not the spring, but it's going to depend on the mass on the other side. So this is the new mass, right? So actually, let's make statements of old and new. So we'll use this. Old, it would just be the mass of P and its final velocity. Okay. Final, sorry if that confused you. Okay. Old, this is the final velocity after the collision. And then we've got Ka squared. New, we've got, well, I guess it's written there, but I'll rewrite. No, it's going to oscillate as a system after the collision. Oh. I guess old doesn't have a collision. Never mind. So it's just the velocity of the oscillation. But when you have the collision, this velocity turns into after the collision. Okay. And so we're trying to figure something out about these A's, right? And so let's go back. We got to consider the momentum equation for the after, right? And so I guess old V of P is just going to be V, right? Well, what about after the collision? V final after the collision of PQ is going to be what? If I solve that momentum equation for V, it would be VF, and I'm going to call it AC, PQ, whatever subscripts you need, right? To know what speed you're talking about. It would be that MP V XI over the system mass. And so after the collision, you've got a larger mass. You've got 3 times the original mass, right? So this is your 3M. No, not squared, momentum. And so after the collision, you've got 1/3 of the speed, yes? And so it would be 1/3 of the initial speed of just P alone. Right? So the speed goes down, mass goes up, speed goes down. Does it net out to be like, well, it's all the same? Mhm. From momentum. I was trying to isolate.
Oh, okay.
Sorry, I'm a little all over the place. I know. So in our old, this is just mv squared. Right? In the new, our combined mass is 3m, and the new speed after the collision is 1/3 of v squared. Does the 3 and 3 cancel, net out to, they have the same amplitude? No, 1/3 squared is 1/9. And so you can look at 3mv squared over 9, or reduces to 1/3. And so look at the energy that leads to the compression or stretch, right? So who's going to have a greater amplitude? Which one? Old. Okay, I thought you said both. So yes, old will have a greater amplitude. And so A old, or P, yeah, just P, is going to be greater than the new amplitude of PQ. Does this make sense? You have to go through momentum to figure that out. You got to know something about that final velocity after the collision. Good deal? Now, I have not written a sentence. This is a paragraph response, right? Now, I don't know if you remember, but last time I told you, last year I was actually part of the grading for paragraph, and at least last year they required a minimum, and this is only if you had supportive work, a minimum of 3. Typically, I recommend at least 5 because they're usually grading for about 5 or 6 things in physics. Now, can you get some credit for the equations? I don't have a diagram, but I did do some equations. Yeah, you can probably get some credit for these. So what are maybe some 3 to 5 big ideas that I should end and write my paragraph? How did we come to this conclusion that the old P amplitude is greater than the new PQ amplitude? I use conservation of energy, so I better talk about conservation of energy. And before that, I actually had to also consider conservation of momentum. And so using conservation, and I would refrain from abbreviating words. I know I do that a lot, and I show arrows for increase, decrease. On the AP exam, try your best to use words. Don't abbreviate, okay? Using conservation of momentum, because usually I say COMO to myself. I haven't done that to y'all, but COMO for me is conservation of momentum, and COMA, center of mass. COE, conservation of energy. So I would just refrain from Newton's third law, N3L, N2L, N1L. Anyway, using conservation of momentum, we determined I determined that VPQ was greater than or less than VP. And I think labeling that, using that expression would be kind of standard, right? They've already identified P and PQ. V is a physics variable. I don't think you need to actually write that expression out. That would be pretty standard. And then using conservation. Oops, I abbreviated again. It's my habit. Conservation of mechanical energy. The kinetic energy, I think KE is pretty standard, of PQ is greater than or less than, be careful on this. What do we say? For the PQ, that's our new one, it was less than the kinetic energy of P alone. And I need to add to that, kinetic energy equals the elastic potential energy. And so the elastic potential energy of PQ would be what compared to the elastic potential energy of P alone? Well, it's gonna, yeah, so this is applying to both situations. But then when you compare just elastic to elastic, our new PQ elastic potential energy would be, well, it's whatever your kinetic energy would be, so it should be less than. A omega is V max, omega squared times amplitude is A max. Those should be back on page 1 of your notes. Okay, so back to our description, one more minimum sentence. I need to connect the energy to amplitude. And so since US is equal to 1/2 KA squared, and K is constant in both situations, then the amplitude of PQ is what compared to amplitude of P alone? Who did we say? Smaller. Are we confident enough to check a box? I know, I write a lot, I do a lot. Notice we don't even really need to consider the energy before the collision, right? I wrote it, who knows, maybe tomorrow they ask about the initial part, okay? And so AP is greater, or I think it's the first one, okay? So let's see real quick where the points went. So I pulled it up. This is straight from College Board. Give me a second. Where is it? Uh-oh. Oh, I had already put it in our key for the packet. And so it's from the College Board website, but I did go on and put it in our new key. And so you can pull that up in Canvas, or it's right. Come on. Let me try again. New share, PDF. Okay. So part A, just 1 point, square root of 3. But don't start thinking, oh, A is always worth 1 point. They don't break it down. So I would still have that supportive work. You never know, okay? By the way, they determine the rubrics after y'all have already taken it. They look it through, 200, 300, 500 samples and make their final rubric, okay? Yeah. So that means part B, your paragraph and supportive work is worth 6 points. And so correct answer, I think that's the one we checked, right? P is greater than, or PQ is less than P. Notice there's no point for checking the box. And it says note, the response is graded even if you select the wrong thing. And so they'll always grade your paragraph, okay? They'll always grade your paragraph. First point, for applying conservation of momentum due to the collision. Did we do that? Check, 1 point. For correctly finding that the post-collision speed, so our new final velocity, has decreased. And it says, or for determining. So did you have supportive work showing that it's 1/3 of the original? Yeah, we did that. Second point. And it says, note, the first 2 points can be earned for stating that the collision is inelastic. So I guess if you didn't have supportive work and you started talking about the inelastic, that it should decrease due to the inelastic collision, you would get a collective point or collective 2 points. Next point, for stating or implying that kinetic energies system has decreased, or for calculating a lower final kinetic energy. We did that. Or it says for stating or implying that the maximum potential energy equals the total mechanical energy just after the collision. I mean, in a roundabout way we did that, but I did the first one. Next point, for stating or implying that the maximum potential energy is reached when the displacement from equilibrium equals the amplitude. Yeah, they said we could use equations. Usually that's pretty standard on the paragraph response. You're never going to have to explain the physics without either talking or using some of the big ideas like conservation of momentum, conservation of energy, Newton's laws, if it was a force type of problem. And so, yeah, I already forgot your question. That's okay. Yeah, they said, that's why a lot of these are saying for stating or implying, or it gives the parentheses, or for calculating. So yeah, most physics people do work.
So if you say inelastic, it will work.
Well, I mean, you could have just demonstrated that it was inelastic to calculate the final velocity. I wrote it out because I write a lot, but you can just demonstrate in your conservation combined mass. That is demonstrating inelastic. Yeah. Okay, and then it says for a logical, relevant, and internally consistent argument that addresses the required argument, yada, yada, yada. That last point on the paragraph responses, y'all, isn't related to physics. So of the 7 points, what's pretty standard is that 1 point is for your communication of physics ability. Can the grader interpret that you have good flow, you're not contradicting yourself? We don't want to say that the PQ combination had less kinetic energy, but then do the opposite or say the opposite when we go to, either check a box or talk about the elastic potential. Okay, PQ has less kinetic, but more potential elastic. That's a contradiction, right? And so that's the logical, relevant, internally consistent. Don't write so much that you start confusing yourself or confuse the grader, right? Try to have good flow. And me personally as a student, I would try to probably be a little neater. Y'all know me, I go all over the place. Okay, as long as you're not, putting your work to page 5 on page 2 and you don't tell the grader, I wouldn't do that at all, right? If you run out of room, you raise your hand and ask one of the test monitors, say, can I have a piece of extra paper? They do have extra paper, and then at the end, it all gets put together, okay? Make sure you put your name or your, y'all are given like stickers. You may be told to put one of your stickers on that extra sheet of paper so that it connects to you. Yes? Okay. So for a total, and here they give an alternate solution talking about the frictional force exerted on P by Q. So this is talking about that heat loss. It's going to slow down. Okay. And then they give a sample. Usually on the College Board released ones, and even the NMSIs, they give not only where the points go, but they try to also give it a sample. Okay. And you can see here, it's a combination of sentences and work. Okay. Okay. So there's that. Questions on the 2018 free response question there. Okay, bear with me. I don't think we'll have time for 2 NMSIs. I'm looking at the clock, but I think we have time for one that's not a spring or not a pendulum. So if you want to work on others, that's fine. I am recording this. You can watch it later. But I told you we do one that's not a spring, not a pendulum. Okay, because sometimes they throw you a curveball, right? So I look at this one and I think, oh, diving board, right? That's not really it's a ruler. This is F2 on page 17. By the way, F2 and NMSI, these are always going to be your lab-based or data-based or experimental-based questions. NMSI always makes them F2. Now, I'll be honest, sometimes that means on the AP exam, Q2 is going to be your lab-based. And that was the way it was for several years, but then all of a sudden one year it was Q3. Doesn't matter which one it is, but it's a lab-based question. These are always going to be worth 12 points. You'll have 25 minutes. So they take longer because they are longer. You have 2 of these long questions, okay? The QQT, the one with new equations and focus on relationships and trends, that's the other long question. Okay, so we have a student given an aluminum ruler. We don't necessarily need to worry about the aluminum piece, but a metal ruler, along with commonly available lab equipment. The student fixes one end of the ruler to the edge of a table. So tape, glue, clamp, whatever. One end of this ruler is not going to move. So in our picture, maybe I can label it here. So our fixed end is there on the table. So that there's a certain length of the ruler, not the whole length, but a portion of the length of the ruler is over the edge of the table. So they're defining L not as the length of the ruler, it's the length hanging off. When the student fixes a small mass to the free end of the ruler, the free end of the ruler sinks down a small distance, y, as shown in the above right. Now, we haven't flicked it yet. We haven't put it in motion yet. What's happening here? This is now our distance to the new equilibrium position, right? When you just set the mass on it and assume it doesn't slide off, then we have a new equilibrium position. The student notices that if the mass is disturbed, flicked, right? You flicked a ruler before. And I'm not going to flick it hard. My goal is not to break the ruler, so I'm not passing these out. Students have broken all my rulers over the years, but you just flick it, right? So they put a mass on, so it's depressed first, and then they flick it. Now it's not going on forever, right? But don't you see oscillatory motion? Video people, I'm flicking a ruler off the table. Okay. I can't video myself and video, anyway. The student notices that when you disturb it from its equilibrium position, the mass oscillates up and down on the end of the ruler. Not forever, but a little bit. The student asks the question, is the periodic motion of the mass also simple harmonic motion? The student determines to perform. The student decides to perform an experiment. Determine doesn't make sense to me. Does it make sense to y'all?
No.
I feel I need to edit. I didn't write these. You know, these are from like a few years ago. I hope they've updated them since then. The student determines to perform, decide. I'm going to say it still works, but I like decides better. I don't know. I didn't write it. I guess they sat there and debated with themselves and they determined that they needed to do an experiment in order to answer the question. There we go. What additional equipment? So they've mentioned the ruler, they've mentioned the mass. What additional equipment would the student need in order to perform an experiment to answer the question? And then So I'm going to do kind of 1 and 2 collectively, and then outline a procedure. You don't have to give every little nitty gritty detail. They've already attached the ruler to the table. I don't need to repeat that. So outline a procedure whereby the student could make measurements with that equipment that we've listed in order to answer the question. And then later, we'll talk about how the student could analyze the data taken during the procedure in order to determine whether the motion is simple harmonic motion. Now I'm going to go in and tell you that lab-based questions usually have more than one approach. The key to NMSI has 3 approaches. So, if I said, hey, y'all try this, y'all may have 3 different methods of collecting data. It's not that one's right, one's wrong, it's an alternative. So what are your thoughts? What would we need to do in order to figure out, is this simple harmonic motion? Is anything coming to mind? Let's brainstorm on the right. Simple harmonic motion. It's not a spring, but we do have a mass. Measure. Okay, so we would want to scale maybe to measure the mass and get the weight of it. Different masses, so a variety of masses. I'm just brainstorming here. Variety of masses. How would we measure that up and down, up and down, up and down? What do we want to measure? Distance. Okay, I'm going to go in and help you out. You only need one. I don't need both, position and velocity. So to me, position's easier. Velocity, you might need to have motion detector. Typically the experimental, you don't want to get too technological. You can. I think another common thing in physics, we don't do it often, but video analysis. I know that when we did a ball drop lab or the flying pig lab, some of you, I allowed you to use your phone for some video analysis, right? The timing of it, positions if you had a ruler nearby. And so I would just start with, basic. How would we measure the position, maybe above and below the equilibrium? Isn't that unique to simple harmonic motion? So what would we need in order to measure that position? Ruler. Anything else? There's one more thing that's pretty important to simple harmonic motion. You could. It is, you could put the ruler to the ruler. That's just the diving board. It's just the platform, right? But yeah, we could also use the ruler to measure the length hanging over the table. Yeah. Isn't timing important to simple harmonic motion? And so to measure time, we would use a stopwatch. Now, if you've listened to me in previous labs, I'm like, ooh, stopwatches, maybe we don't want to time one oscillation. We would want to time several. That could be hard. So I'm going to put a slash here. In physics land, in a perfect world where you're able to do this, you just time it, right? But maybe, slow motion footage, video? No. Timing. Okay, so we got a spirit, right? And I think that's enough. And so we come over here in A, they just want us to list the additional equipment. And so we said we'll need a ruler, we'll need a scale, and we'll need a timer of some kind. Either the stopwatch or the video. And on the AP exam, just pick one method and go with it, okay? What additional equipment? And then outline a procedure, how the student could make measurements with that equipment to answer the question. So we said we'll use the ruler to measure the amplitude, right? Or it's the distance above, oops, above and below the equilibrium location. And then you can also measure the length. Did they say capital L? Yeah. So usually if you use a variable, it needs to be defined either by them or by you. So they define capital L to measure the L of the other ruler. I wish they just said a board, a light board, but anyway, the other ruler hanging off the table. What about the scale? Use the scale to measure the different masses. Do we need the mass of the board, the other ruler? I mean, we could. I don't think we need it. It's going to be consistent no matter what we do. Yeah. And then we'll need the timer or the video to measure the time. And I'm going to go on and, apply it to labs. Like if we really did this as a lab, you'd probably measure the time of multiple oscillations. Maybe 3 to 5 oscillations. And then I think we don't need to, but so we know, and then later you'd reduce it to the time of 1 oscillation. Because that defines what? Period, which is important to simple harmonic motion. And then part 3 says, explain how the student could analyze. So imagine we've collected all this data. What are we going to do with it in order to determine whether the motion is simple harmonic motion? So what should the data look like or do if it is simple harmonic motion? How are we going to analyze it? In physics, how do we analyze a lot of data? Graphs. So I would take the graph approach, right? And so the student can graph what? Period with, what are you going to graph? You got X and Y axis. So let's get a visual here. What do we want to plot with period? What axis does period go on? Are we controlling the period? It's what? So period is a time, and time commonly goes on the x-axis, but here, what were we controlling? The masses, right? So maybe we put mass on the x-axis, and period happens because of those masses, right? And so we can graph the different masses used. Masses used against or with, against sounds so harsh, against the period data. I don't know. And then how are we going to analyze? What should it look like if the objects are in simple harmonic motion? Then the data in the graph would look like what? We'll have, do we want linear?
Oh, well, yeah.
One mass change, like one range, one program, two program.
Should it be a linear relationship?
No.
The bigger the mass, the bigger the period, double, double, triple, triple? No. So it should be, have some curvature. So if the objects are in simple harmonic motion, then the data will have a not curved relationship. What word am I looking for? Exponential. Exponential relationship. So it'll curve up. Now, you don't have to, but how could we get a linear relationship? So this is just kind of bonus for yourself. By the way, last year they had a lab-based question that did have you linearize data. So in preparation with that in mind, what could you plot in order to get a linear graph? T squared. So to linearize, you could do T squared versus mass, right? So just for your knowledge, that would straighten it out if it's simple harmonic motion, right? If your data doesn't support this relationship, then is it simple harmonic? No. There is one more page. We got a little bit left. I'm going to squeeze it in. I know we only have like 5-ish minutes left. Oh, I think we've already done 4. Create an example graph that the student can obtain during the procedure that would indicate. So for us, we already did that. So part 3. I guess I answered both. You literally, if you do the work of part 4 in part 3, just tell the grader, see part 3. And by the way, what I've noticed with NMSIs, if you go to look at the rubric, a lot of times they'll group like 1 and 2 together. Here's what we're looking for. They'll group maybe 3 and 4 together. Here's what we're looking for. So sometimes they're written a little different. Anyway, that's what I've noticed. Okay, so the last piece here, part B, the student then asks the question, does the length affect the period just as it does for the pendulum, or does the mass affect the period just as it does for a spring mass? And so now they're saying, well, you know, maybe up above you only did one of those approaches, which we did, we focused on the masses, but now does the length? So outline a procedure where the student could make measurements necessary to answer their question. And then part 2, explain how the student could analyze the data in order. So we're basically, what's the other thing we could test? So we've already talked about changing the masses. Now we maybe, so the student can use one mass, a single mass, because one change at a time, you don't want to change it all, right? So use a single mass, but adjust the ruler at different lengths. Collect the times again. Oh, and I guess we should have put, you know, good science, multiple trials, right? So collect times again with multiple trials of each length. Okay. Collect, we mentioned the times, and then how could you analyze? So we would do our graph. Does the length variation plotted with times, periods, right? So kind of the same thing, but now with length. And so if it's simple harmonic, then as I'm going to say length could have a direct relationship with T squared. So if it is simple harmonic, so I kind of cut to the chase on that one, right? You would either talk about L and T being that exponential relationship again. Here I went straight for the direct. And so kind of similar to a pendulum, here we're testing kind of the pendulum fit. Oops. And so does it have? Good deal? Now, on experimental questions, a lot of times they'll maybe give you sample data and say, what kind of relationship does it have? That's what they did last year. You didn't have to write out procedures and stuff. So, it's experiment-based, it's data-based, it's all in the spirit of, lab and data. Good deal? All right, the one we didn't get to, I was going to have you all small group this one. I thought maybe there was enough time. F3, so, not that it's for a grade, but this is another long one. Again, we got to be ready for those long ones. They're worth the most points on the AP exam. That QQT. And so this one has you do a little math, and then it's like those students arguing. The student makes a claim. What's right? What's wrong, right? And then it looks like it's another, they make a change, make another claim. What's right? What's wrong? So maybe try this equation, this problem. Key is on Canvas. The NMSIs are in our packet key. One key for one packet is usually what I try to do. Good deal? We do have a little bit of time now if you want to try some of those other multiple choice questions. Page 7 has some, page 8 has some. I know. So multiple choice is important. Don't get me wrong. Half the AP exam, half the credit is from multiple choice. We get a lot of that, right? Our tests are multiple choice. Some of the practice quizzes are multiple choice. By the way, there is a practice quiz, not that it's identical to the actual exam that we're going to take, okay? But if you want some more practice other than the packet, you can do that in Canvas, all right? I think there's some concepts and some mathematical practice. But it's all important. You got to have both types of practice before May 12th. It's 50-50, multiple choice free response.
Could you open the answer for it?
Say again?
Could you open the answer? It's lost.
I did? Okay, yes, let me make that change. Thank you.